Y'all, Barely Berry Jr. back for some more physics. I'll be doing some electromagnetism today, but I think I shall stick with the vertical screen today. So I can keep track of the problems a bit better, but they turn it sideways as well, I'm not sure. Or somebody pops in, you can let me know how it looks to you. Actually, let me go ahead and change it to vertical. And you all end up just seeing a smaller sort of section at once. Just enlarge this. And I'll go ahead and do a few EM problems. The background, as you can see, is this common electromagnetism problem here, which is two concentric spherical shells. Let us pull this from offline as a common problem. And so it says we have two concentric spherical shells of negligible thickness, radii R1 and R2. So from the center of the first sphere to the edge of the first sphere is R1. From the center of the first sphere to the edge of the second sphere is R2. The inner and outer shells carry net charges Q1 and Q2, respectively, where both Q1 and Q2 are positive. What is the electric potential in the regions? So what I'll do here is actually get the electric field and then get the electric potential. And this problem is set up slightly differently than the way we did it in class. A similar problem, but it's not much different. So I'll see if I can work it out. I should end up with similar answers to what I had before. So let me scroll to my notes and I have to end up making a few adjustments. What I'll do is get the electric field, then I'll use that to get the electric potential. So R is less than R1. So that means that the first one will be here. R is between R1 and R2. So the second one will be here. And R is greater than R2. So the last one will be out here. So I'll call these RA, RB. Actually, rather than calling them RA, RB, and RT, I'll just call them A, B, and C. So this is A, this is B, and this is C. As far as the distances that we're going to get the potential at. All right. So to get the electric field, which is the thing we'll use first, is this equation here, which I probably should do better about remembering the names for. But the electric field is going to be the dot product, at least I should say the dot product of the electric field with the area the electric field is emitting from is equal to the charge enclosed divided by epsilon naught, which is a constant of the universe. I remember it's the permittivity of space or the permittivity of the vacuum. I don't remember. It's permittivity or something. If I remember right, it's 1 over 4 pi squared or 1 over 4 pi, something like that. Now, the way we did it before was actually much harder because we wasn't given a charge. We were given a charge density. But it may actually still work out. So the inner and outer shell carry net charges. So when it's positive, so that means that the net charge on here is going to be positive Q1, and the net charge here. Oh, did y'all see that's the only thing about this layout. Sometimes when I scroll, I have to remember to gonna do this. Here, I'll make sure I don't cut off you all adjustment really fast to my setup. Hold tight 1 moment. So you all can see right under the ADA. Set up so you all can see what I'm doing over time. Remind me where the bottom of my writing space is. All right, so that's the equation we can use to find out the electric field. So we know what the charge enclosed is. Easy enough. All we have to do is do the integral on the left, and I believe that's pretty much all we have. Let me just make sure of something here. Enough. So if we look at this integral on the left, we have the electric field and the area. And the way this works is the electric field that's emanating from this positive shell be going like this. It should be at a right angle from the surface. So that means that the surface area that is emanating from the little bitty dA right here that is emanating from, and the electric field, the angle between these two is going to be 0. So you can also call this N and this E. So that means we can simplify this and say it's E dA cosine theta. equals Q enclosed over epsilon naught. So since the angle is 0, that'll just be cosine. And all we have to do now is take the integral of the area there. So one thing we can look at is the volume of a sphere is 4/3 pi r cubed. And the derivative of volume with respect to the radius is the surface area. So that's going to be 4 pi r squared. So now we have E 4 pi r squared equals Q enclosed over epsilon naught. And the Q enclosed, right now we're looking at, actually let me just do this for the general case. So we have the electric field equals Q enclosed over 4 pi r squared epsilon naught. Check and make sure I didn't miss anything. That's it. Now, if we look at the charge enclosed, that will change depending on which sphere we're looking at, which position we're looking at. So at A, the Q enclosed equals 0. So E at A equals 0. At location B, Q enclosed is Q. Let's say that, well, Q1. So EB equals Q1 divided by 4 pi r squared epsilon. Checking our notes, make sure I didn't miss any details. It's good. And for, ooh, so this is interesting. Now, thinking about this, the inner shell carries Q, the outer shell carries Q charge. Both are positive. So that means that the electric field of the inside one is going outward, and the electric field of the outside one is doing the exact same thing. It has its dA element, and the electric field is perpendicular to that dA element going to the outside. It is a surface charge, so the charge is on a conductor. Always goes to the surface, if I'm remembering that correctly. I think I am. Even though it doesn't mention it's a conductor, but usually these things are conductors. So given it's a conductor, remembering correctly, the charge goes to the surface, so they'll have no charge in the inside. Well, I guess technically that could be a surface as well, but usually the charge is on the outside of the shell. Um, if this charge was distributed between the two, the inside should cancel anyway. At least the inside of the smaller one. Because the thing about it is, I forgot all about the fact that we're using a Gaussian surface. So, for instance, the Gaussian surface for the inner circle would be like here for point A. We see there's no charge enclosed in that Gaussian surface. The Gaussian surface for the spot B would be here, and you can see that the electric field would be containing Q1 only. The Gaussian surface would be containing Q1 only. So that's the determiner of the amount of field available from the charge. Now the thing about the outside, the total charge enclosed is Q1 plus Q2. It's a total charge enclosed in the from the outside. Let me adjust my so that means that EC is going to be Q1 plus Q2 over 4 pi r squared epsilon naught. Right. So that should be the electric field in each of those areas within both concentric spheres, between the two concentric spheres, and the last Gaussian surface would be out, out here, of course. Oh, they're actually trying to make a real circle, but this would be the other one. And this would also have its own Gaussian surface and E that's coming out of that. So there we go. What is the electric potential in those regions? So the way electric potential works is page E, the electric field, is the negative derivative of the potential. So we can say that the potential is the negative integral of E with respect to R. And generally the electric field is a vector. So we end up, so this, we have a vector on each one. And the electric field ends up being uh, the vector from the first problem. The electric field is going radially outward. So we could write these like this: negative integral e, a unit vector outward in the r direction, dot product d r, which still gives us the cosine theta and just makes it the e uh, dr or dr. My notes I had it capital. You never recall capital. Well, these are capital as well. So all we have to do now is plug in our uh, equations from earlier, and we can work this out. So for A equals 0, so potential equals um, making sure negative integral 0, the r equals 0. So what we can say then, we could just go back to our original equation. E equals negative dv over dr, which is 0. So that means that negative dv dr equals 0, or dv dr equals 0. So that means that v, potential, has to be a constant, because since the derivative of the potential with respect to the radius does not change, that means as the radius changes, the potential does not change, so it's constant. But there is a potential. We just don't. It's just constant. So there's no um, uh, equation with respect to changing r. So we know we'll have a potential at A. So whatever the potential will be, it'll be whatever it's at A. So we can say that V A equals, well, I should have picked a different, better lettering system. Hold up. VA is VR1. So whatever the potential is at R1, since that's the last place that we have a charge, that potential will remain the same all the way into the center of the central concentric sphere. So for B, we have the same thing. The electric field is negative dV over dr. So dV equals negative integral E r, which equals negative integral. And for B, we have a equation that looks like this. With respect to r. So what we can do here is easy enough integral. So we have getting something, I think. So this potential will be the potential in between to bring the concentric shells back up without scrolling. it'll be the potential between these two concentric shells here, some arbitrary point between those two. So it'll be from, and let me check my notes. I think I did everything differently the first time I did the problem. My conventions for the, what do you call it? Radii, which is totally reversed from this example. So let me make sure I pick the proper thing. Going from basically R2 to B. So the potential here is from R2 to B. So in other words, the potential in this area here, in between the outer shell and the location that we at, that's the only potential that we need to do. So since we're going from R2 to B, integral will have B at the bottom and R2 at the top. So we're going like that. Oh, I think I got to reverse that up. Reverse. B here and R2 at the bottom, which is not such a big deal, but it just changes our negative sign. So what we have here is the negative on the outside. The R here is in the denominator, so it'll be a negative R squared. So that'll go up to a -1 divided by the derivative of that, which is -1. So that changes the sign. So we should have Q over 4 pi R and B R2. So basically we're going from the B2 down to the B down to R2. R2 is our endpoint. Ironically, potential it goes from the outside in. It starts from infinity, which we'll get to momentarily. So that's the starting point. So you subtract the endpoint from the starting point. So that's why B is going first, upward. So then we have, this is V. Yeah, and this is going to be V B minus V R2. So the endpoint is always last. We're going from R2 to B, outward to B. So B is going to subtract that, right? That. That's going to be B minus R2 over 4. Q over 4 1 over B minus 1 over 2. I think that is correct. So then this actually gives us uh, something I did wrong, by the way. Maybe I can call the inner one A. No, there, yeah. Just the convention of everything is reversed from what I did before. Let me check and make sure I didn't miss anything. It's much simpler than I did before. I just want to keep making sure I didn't miss anything because I'm used to more complication. But as far as I can tell, this is correct. Um, check one more thing. Here we can get and welcome those who joined in. Let me know if you have any questions or comments. So in my example, I should have paid more closer attention to the fact that the um, rotation is reversed from the way I did it before. It was like throwing me off crazy. It's probably too late now to like change the labeling of everything to match. So let me just make sure I didn't mix anything up. R1 is what I'm calling my B, what I did before. So one thing I'm not sure about is why my so see, take a look and see how this last one works out. This So same thing. We have E equals negative dV over dr. So V equals negative integral E dr. And so that means that V equals negative integral of this. So ironically, is the same integral, maybe not ironically. It'll just be instead of Q1, it'll be Q1 plus Q2 over. Then we have this one. Actually, it will be slightly different. This is going from infinity to um my old number convention again. We're going from infinity to R2. So it'll be 1 over infinity minus 1 over R2. And infinity, or anything divided by infinity is 0. Let me know if you have any questions about that. That was very strange when I first learned that concept, but you run across it a lot now. At least, I guess I could say at this point, I run across it a lot, many times. So it makes it seem pretty normal now. And I guess I could just put the R2 there. So that means that the potential um, from outside, I guess technically I shouldn't put R2. I should put, looking at my old numbering convention again, what did I call that? C, 2, but C. And this would be, oh, and one more thing I just realized. It goes from infinity outward. So it's C minus infinity, C infinity. So the C would actually be first, and the infinity will be second. That would have changed my sign, so it'll stay positive. So the potential for that part should be Q plus 1 over 4 pi C. And let's see if I did a naming convention mistake on the middle part. I think we're good there. All right, let's take a look at this and see if I mixed anything up. So we should have some continuity here. So let's say the potential for the in the middle. Say we put that at R2. That B might have to use the equation. We put that at R2. C would be R2. So this is basically we're checking for consistency. So it's a test V at 2. C would be R2. So that should be Q1 plus Q2 over 4C. Mm, For the second one, if R2 was at A, B minus A. It's similar to what I had before, except the quantum was so different, a lot of stuff canceled out. So the minus was in the numerator, but it is still pretty similar. Leave that there for now. And we'll go to the other problem I had in mind, which was, I have to draw this one out. So it's going to be a pretty complicated RC circuit. So an RC circuit has resistors and capacitors in it. Let's talk a little bit about what those are. Right. So let's draw this circuit here. And let me know if you have any questions about anything. So this will be our battery. I'll call this a 30-volt battery. So this would be a problem I haven't specifically done. I'll sort of make up the details of it now based upon a similar problem. It will be one resistor, not resistor, I mean capacitor. Let's see, this is 100 microfarads. Let's say that we have two capacitors here. Let us say that this one 200 microfarads and 400 microfarads. And say that we have resistors here. Say we have one here, one here, and let us say that we have one here, and let's call this one 15 ohms. Let's call this one 10 ohms. Let's call this one 30 ohms. And let's call this one 20 ohms. Right. So this is a RC circuit. And we're going to do some physics on this RC circuit here. Right. So what we'll find is what is the power dissipated by the 20 ohm resistor. So first thing we need to do is find out the current going through this thing. And we can do that with the resistors and voltage because V equals IR. So I equals V over R. So we have to get our equivalent resistance. Should be easy enough to do. So we know that the first one is 15 ohms. So we don't have to do anything with that. But the next one is parallel. So if you have resistors in parallel, R total equals 1 over R1 plus 1 over R2, and take the inverse of that. So that means that R call this R1, 2, 3 equals 1 over 10 plus 1 over 20 plus 1 over 30 inverse. And I'll use a calculator to get this really fast. Welcome who joined. Let me know if you have any questions. And this in the calculator. We'll see what this ends up being. So work this out algebra. Just do the math, but I don't feel like doing that. Got to type it in the calculator. So we have 10 plus 120 plus 130. To invert that. So this is 60 over 11 ohms. So that's the equivalent resistance of the three on the right. So then I can go ahead and actually redraw this circuit. It'll look something like this. I want it to be centered better, but let's move it here. Right, I'll delete this first one up here. Delete this down here. And now I have the equivalent resistor here that is 60 over 11 ohms. And welcome who's joining. Let me know if you have any questions. Now what I need to do is combine these. And when you have resistors in a circuit in series, the R total is just going to be R1 plus R2. So, and crap, what is that fraction going to be? The fraction is, I think it's easier to that into, yeah, it is easier to make that into a nice decimal. So that's actually 5.5. That's a bad. I'm rounding a little bit. It's 5.45, but it's 5.5. Right? So that means that the R total is going to be, since those are my two, it'll be 20.5. Nice, almost round number. Seems good. So we can go ahead and rewrite this one more time. And we have one circuit up here now. This is 20.5. That's a lot. Seems like that's a lot. Right? So we're good with that. Then we can get the voltage now. I mean the current now. So I equals V over R, which equals 30 volt divided by 20.5 volts to be ohms, which equals 5. That's something. 5.5. Oh, hold on. That's right. That's the wrong thing. Okay, 1.46. I mean, it seems better. I'll just put 1.5 amp. All right. So that means this entire circuit, we reduce the uh, resistor to its equivalent resistance. When I first closed the switch, when I initially closed the switch, there's 1.5 amps going through the circuit. Right? Easy enough. So now that I have the ampage, we can go ahead and start divvying this up. So the way it works is, I'm going to go back. This whole thing is 1.5 amps. So here we have series resistors, and when you have resistors in series, all right, it's the same, and the voltage adds, if I'm remembering that correctly. So put this as here. So take a look and see what the voltage is going to be between these two things. So V still does equal IR. So V for the 15 one is going to be 1.5 amps times 15 ohms equals, let's see here, that's 21 point, I mean, technically it's 26, 22. I'll round it and call it 22. So I have to round the other one down a little bit. 22 volts. So V 5.5 equals 1.5 amps times 5.5 ohms. So that's going to equal. Now I'll put the actual amounts in my calculator. 8 volts. And as we can see, they add up to the 30 volts. So when you have resistors in series, the voltage steps down a little bit each resistor, such that by the time it reaches the battery source, the voltage is 0. So you can say that when you have resistors in a circuit, the the voltage divides itself amongst the different resistors, which is interesting because that will mean that if you have one resistor, the voltage drops completely with that one resistor, right? You have one resistor, you know, uh, yeah. So what will happen is the current will adjust itself appropriately. So we added more voltage, the amps would have to go up for the resistor value to stay the same, and so on and so forth. So the amps would adjust itself between the voltage and how much resistance is there, which is how we got the voltage, the current we got from the amount of resistance we had. So this is just like having one resistor, and the voltage is still IR. So the current will adjust itself with the resistor to equal up the voltage when they combine together. Which is interesting. I think that's quite interesting. Right. So one more thing. Step this up one more time. Because I want the power in the resistor that's here. So now when resistors in parallel is the same. So that means that V on the 15 ohm resistor will still be 22 volts, but the voltage on all three of these, each of these, will end up being 8 volts. So that means that each of these ones, since they're in parallel, will have the same voltage of 8 volts on each one. And so that's the way that works. Voltage resistors in series, the voltage is sum equal up the total voltage. And resistors in parallel, because they're in parallel, the voltage is the same because they're all connected to the battery directly. So you can see right here, all three of them are directly connected to the battery on either side. So the voltage going through each one is the same. The amperage will change to make it work. And why don't we show that really fast? So we still have V equals I guess I should say I equals V over R. So why don't we do I 30, or let's say I3 equals still 8 volts over 30 ohms. So let's see what this is, and we'll see if this works, if this adds up properly. So that's 2.67 amps. We have 4, let's go up to down to 2. 2 equals 8 volts divided by 20 ohms. So 8 divided by 20 is 0.4 amps. And I1 equals 8 volts divided by 10 ohms. So that's 0.8 amps. So if I add these up, and I'll use the actual numbers in the calculator to add them. That's 1.47. So hold up. Yeah. A little bit of rounding there, but it's pretty much 1.5. So that means it does work out that since the current has gone through this circuit, it's just what it is, like we saw earlier when we reduced this thing down to one resistor, we found out that 1.5 amps is going through this entire circuit. And since the voltage is the same going through each of the resistors in parallel, the current has to be different to make the voltage be the same given the resistors are different. And as we can see, the voltage, oh my gosh, did I add something incorrectly? I think I did. 2.67 now. That's what I did. I put my decimal in the wrong spot when I wrote it down. In my calculator, I put it correctly. So 0.267 or 2.67. In my calculator, I have it. I just moved it over in my calculator. So as we can imagine, the one that has the greater resistance is going to have less current going through it because there's more resistance to it. The one with less resistance is going to have more current. So as you can see, the 10 amp one, the 10 ohm one has 0.8 amps going through it. The 20 ohm one has 0.4, and as the resistance goes up, the current goes down. But all the current going through each one, we add them together, equals up the current going through the entire circuit, because the current going through the entire circuit is just what it is because of the battery and the equivalent resistance. And we'll do one more test. It should work out that the current going through the 15 ohm one is just 1.5. So we'll say I15 equals 8 volts divided by 15. Oh, no, 8 volts, 22 volts. All right. I say, hold on, it's not gonna work. But I calculated earlier that the voltage in the resistors changes. It has to step down, so it's actually 22 volts. It's going to be 22 volts divided by 15 ohms. So it's going to be about 1. So it works out. Of course, physics being what it is, we expect it to work out. That the current going through the entire circuit is 1.5, and it divides appropriately between the different resistors according to whether they're in parallel or series, or in how much resistance they have. Now, the last thing we need to do is find out what the original question was, which is the question I posed to myself, which was how much power is being dissipated by the 20 ohm resistor. And we can do that like this. So we already know that V equals IR. And we can say that power equals IV. So the power in the circuit will be the current times the voltage. Let me check and make sure I'm remembering that properly. Yeah, that's good. So what we need to do is get V inside, we need to get resistance inside power, all right? So all I have to do is plug in this V there. So then we have the power is the current times R. So P equals I squared R. So P is going to equal 1.5 amps squared times, what was I doing? The 20 ohm one? Times 20 ohms. So that means that the power dissipated in that resistor, power dissipated in the 20 ohm resistor is going to be 0. So that'll be 15, should be 30. Looking at that right? 30 watts. And let's check it the other way. So I can actually solve this for I equals V over R. So we've also plugged that in here. This would be power equals V over R times V equal to V squared over R. So should work. Let's see what happens. So the voltage is, what did I call it, 30? I know this formulation works here, but we'll see. And the resistance was 20. So let's see what happens here. Yeah, that seems like that's too much. 45. This is not the way I solved it before. Let's see the way I solved it before. So there's 2. Yeah, V squared R. It doesn't work. We try this directly. Let's see if we get the same answer. P equals IV. So P equals, we know the current is 1.5 and the voltage through the 20 ohm resistor is 8. Let's see what we get here. That'll be what? Is that something must be incorrect somewhere? Getting different answers for each one. Let's see what I did wrong. I must have skipped something. What did I skip? Each of these should, even though I'm not sure about this one, but that one should work. But I didn't do that one early in the other problem. But the other two should definitely give me the same answer. Let's see what I did incorrectly. You know what I did? Forgot to square. Oh my gosh. When I multiplied this right here, I forgot to do my square on this one. So hold up. Let's see what answer I get when I actually remember to square the thing. But I have to put that in the calculator. It's 20. I do get 45. 45. So this does match the one here. All right. So let's see what's happening with this last one then. So the P equals IV. That should give me the same one as well. So what am I doing incorrectly on that one? Oh, current going through that one will be different. Look at that. It'll only be 0.4. Voltage will still be 8. That'll make it worse. So what is wrong with that one? Hmm. Take a look and see if there's anything else I missed. It'd be odd for the top two to be right and the last one to be incorrect. But the fact that the one with the direct P equals IV is so different, it does seem suspect. So the current was, I said the 20 ohm resistor, right? The current is 0.4. Oh my gosh, that's what I did. All right, I need to make my notation a whole lot better. I'm just messing up my notation. So hold up. See what I'm doing. So I need to note this better, which I need to remember for the exam so I don't make this mistake again. Let me do my equations first, by the way. I don't need to actually do my equations. Let me keep these. What I'm doing is I'm putting the wrong values for everything because I'm not properly demarcating what I'm doing. So let me make clear that I'm doing the 20 ohm resistor. The current in the 20 ohm resistor is 0.4 amps. The resistance is 20 amps, but I'll write it again just in case. And the voltage in the 20 ohm one is 8 volts. So now let's see if these all equal the same thing. So we have P20 equals I20 V20. So that's going to be 0.4 amps and 8 volts. So it's going to be what? 3.6? No, 3.2 watts. Just in case. Looks like it's 3.2. 8 times 0.4. Yeah, 3.2. All right. So we'll do, what was the other equation? P equals I squared R. So that's P 20 equals I squared 20R20. So that's going to be 0.4 amps squared times 20 ohms. Let's see what this is. 0.4 is 3.2. All right, so all we got to do is see if this last one works, then I did it correctly. We did P equals IV, we did P equals I squared R. What's the last one I did? Oh yeah, I inserted the I into that. So then I got P equals V over R V, or P equals V squared over R. So we'll do P 20 equals V squared 20 over R. It's going to be 8 volts for 20 ohms. So let's see what this gets me. Oh, 3.2. There we go. So as we can see, even though these equations are wildly different, at least how they look to me, the power that the output given the, not the power output, but the power dissipated ends up being the same. So, and that's how you know that we calculated the circuit correctly, because if you look at the power against the voltage, you look at the power against the current, or you look at the power against the voltage and resistor, look at the power against the voltage and current, or look at the power against the current and resistor, it should all give you the same power if you solve the circuit correctly. So this, I think, is a wonderful example of how mathematical nature is, which is to say that we can represent nature very accurately using mathematics. And of course, if it didn't work that way, then all of our electronics will be haywire. One day you'll turn your computer on and it'll like blow up. You have to get a new computer. The next time we turn it on, it'll be like barely coming on. The next time we turn it on, it'll be changing all the time if things wasn't very consistent. But since nature is very consistent, you get a certain resistor, you get a certain voltage, which is why our outlets in the wall are standard voltage. And your devices have set amount of resistance and some capacitors and so on and so forth. And it'll work the same exact way every time to mathematical precision, within a certain error. Now, the last thing I had to do is determine what did I have to determine? I forgot. Also thrilled and entertained by that part of the problem. I need to find out the current that's flowing through the switch after a certain amount of time. So, looking at the original circuit, and welcome those who joined in. Be sure to drop a line. Let me know if you have any questions or comments as well. Like and subscribe if you haven't. So looking at the current here, the circuit here, if I were to close this switch right here, or say right here, if I was to close that switch, that will start the voltage coming out from the battery, going through the circuit, hitting the first capacitor, hitting that capacitor, going to the resistors, going back to the battery. All the voltage will have, equal 0, and then the whole process will start again. But the thing that we're looking at is that this circuit has capacitors in here, which means that if you look at this is literally a break in the circuit. There's a break. But the way capacitors work is when I close this switch, this positive side of the battery draws away all the negative charges from that plate. All the negative charges are attracted to that positive plate. So this becomes positive, and this becomes negative, and this one should be negative again, and positive. No, I got that wrong. Yeah, and positive, and this will draw the negatives from there, and this will stay negative, if I remember right. Sometimes I get that mixed up, but it's something like that. What's going to happen is, at a certain point, all the charges will move around between the circuits so that, this has only, let's say, negative charge, and this has only positive charge. The flow of current will stop, and then you'll have some fully charged capacitors here, and with no movement of the flow, and the electricity will stop. Which means that means that with an RC circuit, you close the circuit in a certain amount of time, things just stop flowing until you discharge the capacitors. So that means that even though this starts, when I first close this thing, it starts at 1.5 amps. It'll steadily go down until it reaches 0. So why don't I find out at t equals 1.5 seconds. So at t equals 1.5 seconds, how much current is going through the switch. So how much current is going through the switch here at 1.5 seconds. So let's calculate that. And then I may do another problem. We'll see. Or I may get some sleep. I'll see. One of the two. So the first thing we need to do here is consolidate our capacitors. So what I shall do it's a good thing I typed everything down right there, because I could just consolidate the rest right here. So basically, this is our capacitors. So the first thing we notice is the ones at the top are in parallel. So capacitors are the reverse of resistors and how we add them. Capacitors parallel is C, we'll call that C24 equals C2 plus C4. So that's going to be 200 microfarads plus 400 microfarads. So that's 600 microfarads. Hey, what's going on, Riker? How you doing? Oh, RC is a resistor capacitor. So this is a RC circuit. So that means you have a circuit, and the only components in the circuit are the resistors and the capacitors. Actually, that's not the original circuit. Still going to be the same. So RC circuit, you just have resistors and you have capacitors. And sometimes you can mix them up. I mean, I set it up pretty separately because the original product in the class had it separately. I just mixed, I changed things around a bit, the values of everything and the structure of everything a bit. But it should. I guess I don't really know how that works. Maybe that's why they do it like this. Like, in other words, if I put a resistor here, I actually don't know how that will resolve. I don't know if I put a resistor here, will this just be in series with the other resistors, and can we jump across resistors? I guess we have to be able to, because you have to be able to consolidate the resistors into one to get the equivalent resistance. I guess if I did put a resistor here, it would just be in series with these two resistors, and I would just add it in series like normal. It would have to be that way. Oh, understandable. Yeah, I mean, I'm having to learn all this stuff again, and some of this stuff, I can't say I was all that well. I mean, I was much better at EM than I am now, because I was a learning assistant for EM. I'm in school for my PhD right now, and to get a PhD, you have to demonstrate proficiency in all of undergraduate physics. So if you don't know it, if you don't remember it, then you have to learn it again and take an exam on it to make sure you're proficient at it. So that's the only way we can be eligible to actually start working on our PhD officially. So the first 2 years is classes, including showing your proficiency in all of undergraduate physics, and you have to all do all that stuff before you officially get into the research part. So, gotta know it. All right. So we have this. Now, I'm going to redraw this again. Thinking I might be able to take a shortcut and copy it somehow, but it's not so hard to just redraw. All right, so I have 600 microfarads and 100 microfarads. So capacitors in series, they add like this. So this would be C total equals 1 over C 24 plus 1 over C1. And you have to invert the whole thing, right? So that means that the equivalent capacitance of this thing is going to be 1 over 600 plus 1 over 100. Invert the whole thing. So I'll put this in the calculator. Right, so this is 600 over 7 uh, uh, microfarads. So I will go ahead and put it in decimal form now since that helped me before. It will be basically 86 microfarads. That means that now I've reduced all these capacitors to one capacitor. So the equivalent capacitance of all of these capacitors together is an 86 microfarad capacitor. And by the way, if you're curious, or even if you're not curious, if you're just interesting fact, um, the fact that resistors and capacitors combine like this is another one of the ways we can have so many varied pieces of technology, because if you think about it this way, you're like the computer I'm using right now is a different size, a different processing power than, you know, another computer, and even the same computer with a different configuration. So in order to get this computer to work properly and not either explode or just not be able to function because it's not getting enough current, it has a certain specific amount of resistance. But if they made, let's say, one resistor for every single device that needed one, that was the perfect amount. They have to make trillions of trillions of kind of resistors and capacitors and everything else. But what we can do is, if we know how much resistance we need, we can find, let's say if I needed 86, an equivalent capacitance in my laptop of 86 microfarads, rather than trying to find somebody to make an 86 microfarad for me, all I have to do is just find the proper combination of capacitors and put them in my computer in that configuration, and then I have the equivalent of an 86 microfarad capacitor. And the same thing with resistors. You know, you're not going. They only make so many sizes of resistors. You know, usually they have certain standard sizes, and if your device needs something in between that, so if my device needed, what was my equivalent resistance? What did I write to that? Here. So if I needed 20.5 ohms of resistance, I pretty much guarantee you're not going to find a 20.5 ohm resistor in any store or factory. Odd number to make a resistor. But if I know I needed a 20.5 resistor for my device, whatever it is, because everything else that's just what it needs, I know all I have to do is buy a 15 ohm resistor and then put it in series with a parallel group of resistors of 30, 20, and 10. And then I have the exact amount of resistance I need of 20.5. So that's one reason why it's important for us to know this, especially if you're going to be an engineer, Sometimes you might have to do this for your devices to get the proper resistance so your thing doesn't blow up, or because it doesn't have enough resistance, or shut down because there's not enough current because you have too much or whatever. If you just put in a round number of resistors, you're probably not going to end up with the proper amount. All right, so now we have our equivalent resistance. This is 86 microfarads. And what did I need to do with that? Let's see here. So I can remind myself. Oh, and Riker says I've forgotten that you add them up when they're in parallel. It must be thinking of current. Uh, well, I remind myself. Yeah, I believe so. That's right. The current, you do add them up. I have that here. So what this is the current in each of these three resistors, and just like you said, so if I was to do the same color coding I did there, this is the top one up here. I made that in purple. This is the middle one here, and this is the bottom one here. And as you can see, there's about 1.5 amps of current going through the entire uh, circuit here, and the current is added up between each of the resistors, and each of the resistors are here in parallel. So you're correct. That's what they're thinking about. The current is added up between resistors in parallel, but the resistance is not. And that's why, because if you added them up, the resistance won't work out. I guess it's just say nature poses we have to do it that way, else we're going to get it wrong every time. Like I said, you use division when the resistors are in parallel for the current on each side. I don't think I get that second question. I copy these amps, clarify that second question. I can make sure I get that properly. I shall put these there to make this clearer. You can see it all at the same spot. Well, those are the voltages related to that's going through each of those resistors. And as you can see, they add up to the 1.5 that's going through the entire circuit. Oh, right here. Yeah, yeah. So what this is getting the equivalent resistance in parallel for resistors. When you have it, so it's odd because capacitors and resistors are opposite. So, and I remember the first time I ran into this in class, I had problems with it. And every time I was a learning assistant in the class, students had problems with it because it's just, but once you get the hang of it, it, I guess I can't say it makes sense. I mean, it's just the way it is. But I mean, you get used to it. I guess you should put it that way. So I'll make a table for it really fast. All right. So we have capacitors and resistors. You can have them either in parallel or a series. So if you have resistors in parallel, the equivalent resistance is going to be 1 over R1 plus 1 over R2, and take the inverse of that. That's how you get the equivalent resistance. But if you have capacitors in parallel, the capacitance will be C1 plus C2. If you have resistors in series, the resistance will be R1 plus R2. But if you have capacitors in series, the equivalent capacitance will be 1 over C1 plus 1 over C2, and then you take the inverse of that. Oh, no, you're welcome, man. Yeah, thanks for asking questions. So I enjoy interacting. And it helps so the purpose here is to review for me. So yeah, every question you ask, that helps me review as well. So yeah. So keep them coming, no problem. So that's that. That's how that works. So, like I said, I'm gonna be able to go through it pretty easily now because I've been doing it for a while. But it's understandable how it can be confusing because I used to always forget which one is which. I think how I started to remember is I just focused on the capacitors. And if you think about capacitors, if they're in parallel, you have this. They're both touching the battery. So that's the same thing as if you were to touch those capacitors together and you just had twice as big plate. So that's how you could think about it. If you're gonna get an equivalent capacitance of these things in parallel, you see they're just side by side. If you just push them together, you see you just added them together. You just, you know, so that's how you can think about it. Parallel capacitors. And that's how I eventually learned to remember that difference. All right. So we got our equivalent capacitance. This is the part that I had issue with, by the way. I'm reviewing this particular problem because either we never did this in EM when I was in class, or I just forgot it completely. So, all right. So this is the way this works. When the switch is closed, I got the equivalent. Okay, I forgot about this part. We have to get something called the time constant. So we have a RC circuit, a circuit with just resistors and capacitors. So every RC circuit is going to have a time constant tau, and this time constant will be related to the resistance, the total resistance, and the total capacitance. So when I'm looking at this circuit, you imagine I've consolidated everything. So I have my battery here. I have my equivalent capacitor here. And I have my equivalent resistor here. And these things together, like I was saying before, when I turn this switch, so the switch is closed, this capacitor is going to fill up. As it's filling up, the current may slow down rapidly until it gets to zero. So eventually the current is going to reach zero. So in between the time of between 0 to t, at any time point you pull, it'll start at 1.5 amps here, it'll be 0 here, and it'll be steadily going down in between these two. And what I want to know is if this is t equals, what did I say, 2 seconds or 1.5 seconds? What did I say? 1.5. If this is 1.5 seconds, I want to know at that point how much current is going through that circuit. So the first thing I need to do is get my time constant. So the time constant for this RC circuit is going to be, so my equivalent capacitance was what? 86. So this is 86 microfarads. And my equivalent resistance was, what was it? 20.5 ohms. And earlier I did the, I took these units and simplified it, and it does equal up to seconds. But it's ugly mad. Just it's like kilograms. Me is just a whole bunch of stuff thrown up in there. But if I also multiply this together, let's see what we get. We get that times, and I'll go ahead and find the original one. I rounded to 20.5, but let's see what the original one was. The current, for the ohms. So I've done a lot of calculations. First finding that. Oh, maybe I did that one in my head. So I just must be an even number. I don't see it in the calculator. So it's the original thing times 20.5. So that gives me, damn, it's pretty big. 1757 seconds. Damn, so this thing will be running for a while. How long is that? So that's going to be, damn, 30 minutes? Can't be right. So they have made an error somewhere with my seconds here. That could be right as well. I mean, that's one thing about making up a problem. Uh, I might have just made something unrealistic as far as the size of the voltage compared to the resistors or something like that. All right, well, we'll just keep rocking with it. I'll just assume that that's correct. We know the first part is right because I did the current for all the different things. The only reason why I do the currents for all types of different things, but then I do that again. Here, I can ensure that works out. So we know that the current is fine. The voltage is given. So, I mean, I guess it just is what it is. Even if I still can't see how that would take that long, so I probably just use values that are not good for this circuit, but we'll keep going. At least we'll see how the process works. So, next thing we have here, I have my current. And for the IC circuit, the time goes like this. IRC at T is going to equal I naught, and hopefully they give us this equation in the exam, negative T over tau. So I can use this to find out the current at any point in time. Oh crap, that makes sense. So I forgot, I wasn't remembering what the actual equation was. So what's going to happen is when I plug this in, this is going to be 1.5 amps e to the negative 1.5 because I want IRC 1.5. So, oh, okay, so that makes sense. So that means that everything worked out so that I just have a whole lot less time since compared to my other, the one that we were given. So I must have added more resistance, which makes sense. I think I simplified everything but made the numbers bigger. So let's see what this gives me. 1.5 times e to the negative 1.5 divided by that, let's call it 1757. Damn. All right. It went down a little bit. Yeah. My numbers are just off, I think. Like my original numbers. I'll check and make sure. I got like 1.49 something. Yeah, so that would make it take a long time. So that'll go in the denominator. Very small number. Okay. Let's see what I did wrong. Let's see if I did something incorrect here. Because either I did something incorrect or my numbers are just, when I made up this problem, I just used some crazy numbers. And this will not, like, these numbers won't work in a regular circuit. The time constant. Oh my gosh. I see what I did. This is microfarads. I forgot to convert it to micro. That's what I did. Oh my gosh. Newbie mistake. Gotta remember that one for the exam. All right. So this microfarads is going to be e to the negative 3 farads. So that's what I forgot to do. So this will be 1.7. That's what that is. So that means that this will be this. All right, so let's see what this answer is now that I put my decimal there. Decimals will kill you. All right, that makes sense. All right, that's better. So this is saying that after 1.5 seconds, when I put this in the calculator, after 1.5 seconds, the voltage going through the current, the circuit will be 0.64 amps. Okay. All right, that's reasonable. So we started at 1.5, right? Was it 0.64? We started at 1.5. Original one here. So we started at 1.5 amps. This is going through the uh, circuit as a whole. I equals 1.5 amps. When I initially close this circuit that somebody is going through, the capacitors, I close the circuit. This is the positive side of the battery over here. It's attracting all the negative charges from there. So this becomes positive as well. So this becomes positive. This becomes negative. This becomes negative. This becomes, this becomes positive. This becomes positive. This becomes negative. This becomes positive. This becomes negative. Yeah. The negative. I think that's how it works. Yeah. So then eventually all the charges will move. The current stops. It'll eventually reach zero. But at 1.5 seconds, it'll only have gone down from 1.5 to 0.64. So let's see, how can we find how much time it'll be till it hits zero? I mean, of course, an infinite amount of time. If you think about it, right? If we have IRC at infinity, this will be 1.5 amps times e to the negative infinity divided by, doesn't matter what that is, because this will be like a huge number, but it'll be 1.5 divided by infinity. So it'll be zero. So we know that at infinite amount of time, there's zero current going through it. But what is the first instant it hits zero? It's going to be hard to calculate. I don't know if this is a set thing. It probably has to do with the circuit and the, I mentioned earlier how everything happens to mathematical precision given an error. We don't make our devices perfectly, and so on and so forth. Um, the wires, the current, there's a little wiggle. So at different times, each time you do it, it'll probably be a little bit earlier or later that it actually hits zero effectively. Pretty sure there's a way to calculate when it first hits it, but I don't know that. I don't want to try to figure that out now. I guess I'll go ahead and call it. I've been going for 2 hours, 2 problems. The first thing I did was a 2 concentric spheres, which is the background I have right now. We found the electric field and the electric potential, which I may have made a mistake on because it was so different. I didn't realize the problem was so different than the one that we did in class. Like the charge was given just as a charge. I didn't have to calculate the charge, which did simplify it. But because I didn't have to calculate the charge, I couldn't cancel as many things in the final answer, and the notation was different from the one in class, so it kind of threw me off. So maybe some errors in that one, but the general process was right. And this one, the second one we did for the RC circuit, I changed the circuit around, but everything seemed to make sense. So we calculated the voltage for the current for all of the resistors, calculated the voltage for all the resistors, it all added up. The numbers at the end made sense. I'm pretty sure that was done perfectly. The RSC circuit one. So those are the two problems I did today. What I'll do on Saturday, I'll actually go back to graduate physics. So this is some undergraduate physics. Saturday, I'll go back to graduate level physics and we'll do some classical mechanics. So be ready for some heavy stuff on Saturday. I know some like doing more complicated problems. I've gotten some appreciation on that. So we'll dig into some more complicated problems on Saturday. Graduate level stuff. We'll be back before Saturday, but definitely by Saturday. But just make sure you subscribe and hit the little bell thing so you can get notifications if I'm doing impromptu like I did today. And but the rest of the week, be some graduate level stuff. So y'all see some interesting stuff. Thanks for commenting, Riker. Good to see you. Thanks for everybody who else who joined as well. And I shall see everybody next time.